about linear programming, which is a method for solving problems where a particular quantity must be maximized or minimized, but it's subject to certain constraints. So we've got a couple of features of these linear programming problems. One is what's called an objective function. And the way you can recognize that is it's your equation. And your objective function problems will either be maximized or minimized. So skipping down to number 1 just for a moment, it says suppose we want to maximize z equals 10x plus 6y. So this guy is my objective function. Right, and our goal is to maximize the value of that objective function. All right, also, each of these problems will have what are called constraints. And you can recognize these because there'll be a system of linear inequalities. So down below, we've got the constraints 20x plus 10y less than or equal to 80,000, x plus y less than or equal to 6,000, and then x greater than or equal to 0, and also y greater than or equal to 0. So those guys are my constraints. The objective function is an equation, constraints are your inequalities. So to solve a linear programming problem, first you graph the system of constraints. So actually, let's just go ahead and do that, and then we'll get to step 2. So the first step is we want to graph this system of constraints. All right, so I'm just going to solve all of these for y if they aren't already. And actually, before I do that, these guys are typical constraints, x greater than or equal to 0 and y greater than or equal to 0. So if I were to graph those, they're two solid lines. There and there. And at this point, it's just restricting us to this quadrant, right? So I'm going to undo that shading, but you'll see these quite often where you have x greater than or equal to 0, y greater than or equal to 0, and all that's doing is restricting you to that positive quadrant, quadrant 1 so far. All right, so let's fill in the other two constraints here. So solving this first one for y, I have 10y less than or equal to negative 20x plus 80,000. And then I'm going to divide all the way across by 10, so that gives me y less than or equal to negative 2x plus 8,000. All right, so my y-intercept is 8,000 right there. And then my slope of negative 2, I could think of that as negative 2 over 1. Or I could even think of that as negative 2,000 over 1,000, right, given this scale. So for my y-intercept, if I go down 2,000, then I go to the right 1,000, down 2 to the right 1, down 2 to the right 1, down 2 and to the right 1. And with these constraints, a lot of times it'll be really helpful to go all the way down to the y and x intercept. So I'm going to go ahead and graph this using a solid line. And y less than or equal to right now would put us in this shaded region, right? So right now we're inside this triangle. We're greater than or equal to, x greater than or equal to 0 and y greater than or equal to 0. But also we're below that inequality that we just graphed there. So I just want to mention that. All right, and then finally, let's take our last inequality over here, x plus y less than or equal to 6,000. I'm going to, oops, didn't mean to erase that. I'm going to subtract x from both sides. So, sorry, it's getting a little messy. So this gives me y less than or equal to negative x plus 6,000. So there's my inequality to solve for y. So plotting my y-intercept 0, 6,000 would be right there. And then my slope is -1. So down 1 and to the right 1, down 1 and to the right 1, down 1 to the right 1, down 1 to the right 1, down 1 to the right 1, and down 1 to the right 1. All right, so you want to draw these constraints very carefully so that you can see exactly where your system of inequalities are. And that's also less than or equal to, less than or equal to. So this is putting us right here in this little quadrilateral, if I shade inside there. Okay, so that's our system of inequalities, and now what we need to do is identify the corners, okay? So we're gonna graph the system of constraints, and then we evaluate the objective function at each corner or vertex of the graphed region. So that's our next order of business, is we need to identify each corner. So we've got 0, 0, the origin, that's a corner. And I've listed them down here, so there's 0, 0. Another corner is 4,000, 0 right here. Also, these guys intersect at 2,000, 4,000, and I can see, just because I've graphed really carefully, that that's where they intersect at the ordered pair 2,000, 4,000. And then also in the top left, the final corner of that shaded region is 0, 6,000. So those are the 4 corners of my constraints. And now what I need to do is evaluate the objective function at each corner. So that's the final set of instructions. Evaluate the objective function at each corner or vertex of the graphed region. And then the maximum and minimum value of the objective function will always occur at the corner points. So remember, we had the objective function z equals 10x plus 6y, which is rewritten down here. I'm going to evaluate that objective function at each of these corner points. So first for 0, 0, z equals 10 times 0 plus 6 times 0, which equals 0. So that's our first value. Next, at the ordered pair 4,000, 0, I have 10 times 4,000 plus 6 times 0, which gives me 40,000. All right, next up, at the ordered pair 2,000, 4,000, 10 times 2,000 for x plus 6 times 4,000 for y. Oops. There we go. So this gives me 44,000. And then finally, we have 10 times 0 plus 6 times 6,000. And that gives us 36,000. All right, so these are the values of our objective function at all of the corners. And remember that we're trying to maximize, our goal was to maximize the value of the objective function. So looking at these 4 numbers, 0, 40,000, 44,000, and 36,000, of course the maximum is 44,000. So we can say that the objective function function's maximum value equals 44,000, and this occurs at the ordered pair 2,000, 4,000. So the max value is 44,000, and the location at which this occurs is the ordered pair 2,000, 4,000.